A doctor is scanning a digital mammogram, looking for the faintest sign of an anomaly, but the vital details are buried, hidden completely within the darkest pixels of a scan. The instinctual fix is to simply turn up the brightness. In image processing, we call this a linear transformation, applying the exact same mathematical increase to every single pixel across the board. But when you push every value up equally, the few spots that were already bright crash into the absolute pixel limit. They flatline into pure white, destroying the image before the dark details ever become visible. We are left with a mathematical vacuum. We need a way to selectively stretch out those dense black shadows while leaving the already bright areas completely alone. To reveal what is hidden, we have to abandon linear changes altogether. Instead, we use point operations, mathematical algorithms that evaluate and alter every individual pixel based strictly on its specific starting value. For severely dark images, the primary mathematical tool is the log transformation. This chart shows the exact mathematical curve of the log transformation. You can see the input pixel values across the bottom axis and the resulting output intensities along the left. Look at the left side of this curve. A very narrow cluster of low-intensity dark pixels is aggressively mapped upward. They stretch out across a massive section of the output scale, turning compressed, unreadable black shadows into a broad, highly visible range of grays. Conversely, the higher intensity bright pixels are severely compressed. A massive jump in the input value results in almost no upward movement on the output scale. This guarantees the lighter pixels don't blow out into pure white. This specific, highly uneven geometric curve is exactly how we rescue trapped data. It forces the darks out into the light without sacrificing the rest of the image. When we write this into code, the log transform formula looks like this. But notice the +1 inside the parentheses. Why do we need to mathematically add a 1 to the starting pixel value? A pure black pixel has an intensity value of exactly 0. In mathematics, the log of 0 is infinity. Without that +1, an impossible calculation would crash the computer's output immediately. Then there is the C at the front, the scaling constant. Our physical screens are rigidly hardware constrained. A standard 8-bit digital image displays exactly 256 shades, ranging from 0 to 255. That constant is calculated to compress the wildly expanded new mathematics back down. It mathematically ensures that the absolute maximum pixel value hits exactly 255, allowing the data to actually fit on your screen. If we face the opposite problem, an overly bright, washed-out scan, we reverse the mechanism. An inverse log transform is applied to compress the light values and expand the darker ones. We also use the gamma transformation, or power law, to fine-tune overall display contrast. Setting the gamma below 1 specifically enhances dark grays, while setting it above 1 targets and enhances the light grays. These algorithms rigorously normalize mathematical extremes, so the data can actually survive the physical hardware limitations of our displays. Which brings us back to the unreadable digital mammogram we started with. The moment the code executes the log transformation over that raw matrix of pixels, the shadows fall away. The dense internal structures and any potentially dangerous anomalies are perfectly clear to the doctor. A diagnosis can begin. These specific point operations are executing constantly inside our smartphones, televisions, and digital cameras every single day. Mathematical formulas like log and gamma act as invisible translators, taking vast arrays of unreadable raw data and reshaping them into something human eyes can actually perceive.